Okay, so topic of today. Basically, we're going to figure out how long that timeout should be for our reliable transport protocol. And then if we figure that out, finish that, then we'll start thinking about how big the bandwidth is of this pipe. So basically, if we want to go quick, right, if we want to do a fast transfer through an unreliable network, we need to know what is the latency, both so we know when it's time to retransmit, in case we don't get any cumulative acts, right? And so we know, in combination with the available bandwidth, so we can figure out the bandwidth delay product, right? Which basically says how much information should we stuff in this pipe before we start waiting for an ACK. That determines the capacity of the entire path to the destination. All right, so we need to figure out two pieces: latency and bandwidth. And so for latency, basically, we have some measurements, right? We send a packet, we get an ACK back, and we need to now get a pretty good estimate of what we expect the latency to be for every new packet, and also sort of what should be the limit, right, of when do we give up on a packet? When is it time to retransmit? So we want an expected latency, and we want a standard deviation or something like that, and then calculate a timeout for each packet. Maybe we call it expiry time. Okay, so what's the input that we have here? I guess initially, before we've sent any packets, we don't know. Right? We have no idea what the latency might be to an end host. If the destination is nearby, which you can't really tell by the IP address, it could be as little as about 1.5 microseconds. Right? That would be an extreme example, and then on the other end, it could be as much as several seconds. And so we said earlier that we start with a guess of 3 seconds. This is just what you basically have to pick a number. So we send a packet and we see, oh, it didn't come back after 3 seconds. And then what? Should we try again? With 3 seconds again, or? What's that? It's probably better to up it, right? Because it could be that this destination is further away than 3 seconds. We didn't just lose the packet, but it's hard to tell which it is at the moment. So if we lose a packet, double the wait, right? Or let's not lose if we don't get a response within expiry date. Right? So now, at least we know we're going to send a fairly small number of packets before we've reached the actual latency of this destination. So we could start much lower, of course. Most of our destinations are less than 3 seconds. There's some trade-off there. But I think TCP at least goes with 3. It's good to be conservative because we don't really know this machine that we're running on right now. We don't know how it's connected to the rest of the world. It could be over a geosynchronous satellite, and those have pretty long latency. I think it's on the order of, let's see, it's about 20,000 kilometers away. So 20,000 divided by 300,000. Okay, so it seems like just going to the satellite isn't so bad, right? About 120 milliseconds round trip. So that's not why they're considered slow. It must be something else. But in any case, there's many cases where you would have a slow link, and in those cases in particular, you probably don't want to fill the pipe with a bunch of unnecessary packets. So we should start out nice. And if we have a good link, well, probably we get a response in much less than 3 seconds. Or if we sent the packet and we didn't get a response, then it's because we lost the packet. So if we lost the packet, we probably shouldn't be sending so many packets anyway, because the network is probably quite congested. Although it could be that you're on a poor wireless link. Right? So you send to a nearby destination, you try to connect, like send your first packet, you don't get a response. It actually responded really quickly, but you lost it on a crappy wireless link. Right? That happens. Those links are fast. Like the packet, if the packet makes it across, it'll go in microseconds or milliseconds. But let's leave it at milliseconds. But you could be very likely to lose some packets. So there's a trade-off there. If you have a very lossy link, this is probably not such a good setup. And TCP in general is not so good for very lossy links. See some alternatives later on. Okay, anyway, so we try something, and then we actually get our first packet back. We get a measurement. So we don't care about what's in the packet, right? But when we sent the packet, we see what time it is, and then the packet comes back and we see what time it is, so now we know what was the latency for this packet. So how long should we wait for the next packet? Right? You could say, oh, wait X milliseconds, right? But then half the packets, assuming X is an average here, it's a pretty good guess. X is the average time it takes for a packet to get around. If you're going to make a guess, that's a good guess. But it's still not very accurate. So probably about half the packets would not make it within the deadline. So what should we pick instead? Yeah?
2x.
2x. But we don't have any idea what the standard deviation is. It could be that the deviation is greater than the... Well, yeah, okay, 2x. Fine. For the first packet, why not? Let's do that. All right, so we get another packet. Right? So that's x2, that's the second x. So probably now we want a mean, maybe, right? It's good to estimate the mean. And we can also calculate the deviation at this point. We have if we take the difference between this and the mean, and this and the mean, like take the mean of the means, there's your deviation. Sorry, mean of the differences, there's your deviation. So, okay, that's pretty good. But unfortunately, the internet isn't just going to stay the same all the time. So sometimes a link gets more traffic and there'll be a longer latency. Or sometimes you move your laptop closer to the access point and you get fewer retransmissions on the wireless link and you get lower latency there. So things change. So you can imagine now if we have a long transmission. We're sending packets back and forth, back and forth. So we keep aggregating this mean. Right? We've sent 1 million packets. And then suddenly things change. So it used to be 100 milliseconds, and now suddenly it's 120 milliseconds. We have to catch that, right? But we've sent 1 million packets, so it's going to take a while before we catch the fact that it's now 120 milliseconds. So we somehow need to have a mean that varies more quickly, right? You can't just take a mean over all the packets. You have to do something different. So there's a couple of solutions. One is called a sliding window average. So you could say, oh, let me compute the mean over the last 100 packets, right? Or the last 1,000 packets, and the standard deviation over that. It's pretty good. But we don't really know how long the window should be, and it's kind of expensive to compute that, because then you have to remember the entire window of delays in order to compute the mean. There's no other way to do it, really. and yet another alternative, which is stateless, almost stateless, very cheap. Does anyone know? What's another kind of mean we might use? It's called an exponentially weighted moving average. Heard of this? Okay, so I figured we'll do some experiments with this. The general idea is, our mean is, let's see, it's called the mean 2 is the previous mean times the previous mean plus 1 minus alpha times the sample. Right? So alpha is between 0 and 1. General idea is we want some of our history, like what the mean used to be, and then we want to add on, for the rest, we want to take our current sample. So if alpha is 0, then the mean is exactly the most recent sample. That's it. Right? And if alpha is 1, well, then we're ignoring the most recent sample. We're all based on history. So none of those are very good means. If then we pick alpha as a half, then the sample before counts as half as much, right? And the sample before that counts for a quarter, and the sample before that an eighth, right? So now we have a pretty short slope of this thing. So we're ignoring the distant past. So you can kind of tweak this thing. But let's get a little more concrete. I thought we'll just do some pinging. So we'll do New Zealand because I like those long round trips. Right. So you see here, the latency is varying quite a bit. This is much better on the Wi-Fi. It's not mostly the Pacific Link's fault. It's mostly ACCC's fault, or maybe your fault. Maybe someone here is watching movies. I don't know. Anyway, the latency is varying by a great deal, over 10% on every sample. So this is going to be great. All right, and there we lost a packet even. Okay, so how can we make this more interesting? I want to try to plot this stuff live. Okay, so the column we want is 1, 2, 3, 4, 5, 6, 7, 8, 9. The 10th column. And I just happen to know it'll work better this way. Guess it didn't work better that way. Really? Okay, we'll go with a higher, quicker interval, and then maybe. What am I doing wrong here? Okay, that's working. Did I count this wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I will just pipe this into a file. Sometimes the terminal can be a little weird, so we'll just try this and see if it shows up in the file. Or it doesn't want to. Let's see. It's really awkward. Maybe I should go with gawk. Oh, come on. All right, we'll just do it this way. awk is somehow deciding to buffer my stuff, and it doesn't want to output it to the screen, and I don't understand why. There's ways to tell it, like, oh, I don't want you to buffer, but I forget how. So we'll just do it this way. Okay, so they're ending up in my ping file, and from there now we'll be good. So I'll just say do the processing here instead, make it a little bigger. And I want you to pay attention to what's going on the screen here, because these are really handy things to know. You know, maybe not the ping part, but the processing stuff. And, maybe we'll try to do some sort of assignment on this later. I don't know. 10, right. Okay. What the hell? Okay. I wanted to do something live, but I think we're going to have to go static and boring like this. All right. So these are the values. All right. We can still manage. Okay, so I'm forcing it. So we're saying here, I just want the 10th column, right? I don't know why awk is being so awkward with these streaming things, but now I'm just running this every second. So now we should have an update on this every second. Okay, good. So we want to plot that stuff. So these are our ping times. Let's try plotting it. You would do it something like this. All right, so there they are. And you see they do vary quite a bit over time, but we want to do this, try to make this a little more live, so we'll do it this way instead. So we'll print this over and over. Go like this. So GNU-plot is this thing, you just give it a text file, it'll by default plot the values in the first column, and you can tell it formulas and all sorts of stuff. I'm going to tell it, give it some commands on the fly here. Basically plot, plot, plot. Let's see what the commands look like. Like this. Right? So now we should be able to pipe that through GNU-plot, and then maybe get. All right. Okay. So there it is. The measurements are coming in. See if it hopefully will change the plot when we get to the edge. Come on. Yes. All right. That looks nice. Okay. So we're getting there. We just want to compute the mean and the standard deviation, and maybe see what it. If we can come up with a good mean. So I'll just leave this running, and we'll start computing some new means instead. Right. So I'll say like this, like the mean equals mean, let's see. So actually a recommended value is 0.1, let's see, what is it? 1. There. So 1/8. So we take like 7/8 of the old mean, and then 1/8 of the current sample. That's sort of how we average the two together. Let's see what it looks like. So there's our mean, and then plus $10 times $1, right? And then we plot. What am I saying? $1. 0.125 right, times $10. Okay, good. So now we have the mean as well in our output. Oh, that looks bad. It doesn't like my comma. Okay. Okay, let's see what it looks like. Plot. Oh, did I not? I said plot. I should say print. Okay, that's more like it. All right, so now we have the two values, right? The samples and the means. It's still just coming out with the samples, but we tell our GNU plot to plot the mean too, and we're gonna be in good shape. So like this, 1, and then all right, so that's starting to look like something. Let me start over the data collection just so we don't have so much data and start looking a little more interesting. Right, okay, so here's our UMA. Like it starts at 0, right? Because we didn't initialize it. But then we get these samples from New Zealand, and it's kind of getting to the mean. Okay, so we can't really rely on this, right? Because this is the mean still. If we wanted to kind of come up with a timeout, we can't very well go with 2 times this. Right? Then we're at 500 milliseconds. That's going to be awful. So we need to kind of estimate how much does it usually vary around the mean, and then go some function of that. So one way to think about this is, let's pretend this is a normal distribution, a bell curve. So if it's a bell curve, the width of the curve is determined by the variance of the samples. And so if we take 1 standard deviation, I see a lot of blank stares here. So let's pull up the bell curve. Here. It's actually pretty important stuff. So, okay, so it looks like this. Right, so if we compute the standard deviation here, right, how much does it usually vary? What's the average deviation between our mean and our samples? So if we say, oh, we're within, and this is two-sided, but okay. So now within 1 standard deviation is this much of the curve, right? If we assume this is a normal distribution, which is kind of a weak assumption, or a strong assumption, I should say. But anyway, so we clearly should not go with 1 standard deviation out. And we probably should not go with 2 standard deviations out. But now when we start looking at 3 standard deviations out, it's pretty rare that you would find a sample that falls outside of 3 standard deviations. So maybe we can live with losing those samples, even though they actually made it around. Like the packet maybe just got delayed unusually long, and then we eventually got the ACK, but maybe we can live with retransmitting them. That's sort of the trade-off we're making here. Actually, it might be better to go a little bit more, and that's what TCP does, because it's not really a normal distribution. But so they go with 4 times. So we can compute that too. So let's try to tack in the, it's going to be a little more challenging. Let's see. So we want to compute also the deviation. So the deviation is, let's see, if the sample is smaller than the mean, And deviation equals the previous deviation. And these are just the constants that they're using in TCP, so I'm going to use the same thing. Can you see that in the back? Not really? All right. So we're using, for the deviation, you want to adjust a little faster, apparently. So we go with a 3/4 for the history and a 1/4 for the current. So it'll be, okay, so if it's smaller than the mean, we should go 10 minus mean like that. Right? Else d equals no, I did it wrong, didn't I? Yeah. If it's bigger than the mean, it should be this. Okay. Okay, so now we're computing the mean. We have the sample, the mean, and the deviation. So we'll just print all of those out. I think the plotting will look the same for now. Let's just start this over again. Did this start getting a little more reliable? It kind of looked like we stopped having so much deviation, but okay. So now we've got this running, but I want to tell it to plot also the deviation. So let's see. Actually, this is going to get pretty lame because the deviation is really small. But let's start with that and let's see what it. I think it's not going to plot very nicely. Oh. Oh wait, overriding here. Okay, that. Okay, so I put a title on it too, and this should look nice. All right, so you see, here's the deviation. So every time we get a weird sample, the deviation grows a lot, right? This was a really strange sample here. Seems like there's something a little wrong with our math. 0.75. No, okay. Just seems to me like it's going up more when you're dipping down than when you're going up. It's deviation. It's a little surprising. I don't know why we get, every now and then we get one of these that takes only 200 milliseconds, and for the rest is 230. That's a really funny latency measurement. Okay, so anyway, that doesn't seem all that useful, but now we know how much does it usually vary around the mean. So then we can compute what should be our timeout, right? 4 times that standard deviation. That'll give us some margin so that we usually don't miss our samples. So why don't we put that in the plot instead? I'll just do it here. Using 3, let's see. So you do it like this: 4 times the deviation plus the mean. So, come on. Ooh, that wasn't right. Okay, I feel like I'm getting lost in all the escapes here. So let me back this up and we put it in here, and we'll do the computation in here instead. 4 times mean plus, no, deviation plus the mean. Okay, good. Start this over, start over from the beginning, get some fresh data, and we plot just the timeout. Right, okay. So this is starting to look like something. Whoa, we got some crazy samples there. What is going on? So when we have some crazy measurements like this, I don't know, maybe there was a big short file transfer, or someone, I don't know, started a microwave oven or something, screwed up the Wi-Fi for a bit. Then this here, the timeout, it gets really generous, right? We've seen that there's weird stuff going on, so we're generous, but then as things get more reliable, then we pick a pretty tight timeout. In fact, let's change the plot so we can get a little better resolution, maybe plot it from 200 to 300. Gnuplot is a fantastic tool, and so is Bash. Okay, so now we got a little more resolution. All right, so this is actually what TCP does, except it doesn't ping, right? It sends packets, and then it sees, oh, I got the acknowledgement this time, and so I need to adjust my timeout for the next one of those. Every now and then we're losing a packet here, and I'm not dealing with that in our calculation. I think if you have a window, it doesn't make sense to double the timeout. But if you only have one packet outstanding, well, then we really need to restart we need to double the timeout, so we make sure that we're not sending too many packets. But if you're getting most of your packets back, you don't want to double the timeout and go crazy like that. I'm not actually sure how we would deal with a lost packet if it's actually lost. I think the best solution is probably to just remember the packet, see if it comes back a little later. If so, adjust appropriately. If it's actually completely lost, well, then we better just ignore it, I would say, in a window situation. All right, but you see, this is what the internet is like. I don't know how much we want to blame the wireless channel and how much we want to blame the rest of the network. I think it's mostly the wireless channel, honestly. Okay, questions? Okay, no questions. So you see, we will miss a few, right? Every now and then there's a surprise. Like here, I updated, this is cheating. It looks like I increased the latency like just in time for the sample, but of course I increased it after I received the sample. So we would have missed this one. We would have missed this one because that's the measurement that increased the timeout. Okay, so I think that probably settles the determining the latency. Now, what about how many packets we can send? I better stop this now. I think it's too distracting. Okay, see if you can reconstruct this thing at home. You know, you don't maybe have to do it live. You can collect a bunch of ping times and see if you can make a plot out of it. Gnuplot is really easy to install. This is just apt-get install, apt-install Gnuplot these days. And for the rest, there's nothing here. Everything else is already on your command line. Okay. Right. So now we know how long we should wait for a packet to come back. But really, if we wait, if we want to transfer something to University of Canterbury here, every packet, the biggest packet we can send is 1500 bytes, all in, with headers and everything. So does anyone want to compute, if we have one outstanding packet at most, what is our maximum throughput to the University of Canterbury? Okay, so this was minus 0. And here, mean plus 4 times def. Okay. Total throughput to the University of Canterbury. 1 outstanding packet. By outstanding packet, I mean we have sent 1 packet and we're waiting to hear back from it before we send the next packet. We can't just send an unlimited number, because then there's a good chance that we would just be sending stuff that gets dropped along the way. So we need to track each one. How many should we track? We'll have to find that out. But let's say we only track 1 at a time. What can we expect to see? What throughput can we expect to see? Anyone?
5 kilobits per second.
5 kilobit per second.
1200 bit packets, right?
Well, 1500 bit packets. Byte, sorry, byte.
Okay, sorry. Then 5.2 bit.
Yeah, the total throughput is packet size, right, divided by latency. So in this case, we got, if we just figured 1500 bytes, that's a little generous because there's some headers in the way, but 1500 bytes, and then divide by, what was this? It was about, let's call it 250 because it makes the math easy, right? 0.25, so that's equal to 6 kilobytes per second. Very good. Right, or about 48 kilobit kbps, right? Okay, I guarantee you that we can do faster transfers than that to New Zealand with TCP. So in order to make that work, we have to have more than 1 outstanding packet. So then the question really is, how many outstanding packets? The problem we could run into, I think I should draw it. And this is a likely problem to encounter, that we would encounter, is here are we, and here's our destination, and there's some routers along the way, usually many, right? Actually, let's, just for the heck of it, okay, there we're having a timeout. Let's see if I can tell it. I want a shorter, minus D, maybe? No. What's the timeout? W. Okay, we wait for half a second. Oh, really? Is it maybe in milliseconds? In seconds. It's not nice of them. All right, we'll go with 1. Right, so we're in San Francisco, and now we made it straight from San Francisco to New Zealand. Apparently the one we're using does not go through Tahiti. Right? I was showing these links that go to Tahiti and then on, but it looks like at least there's not a router in Tahiti. Maybe they just ran the fiber straight through the same pipe, right? I'm not sure. In any case, this looks like there's 2 optional routes here, and we were about 14 hops until we make it to the destination. So somewhere along here, it's slow, right? We're in Chicago, and now we make it to the west coast, and now we're in New Zealand, right? That's the latency. We can't blame latency for a throughput problem, because throughput is the combination of the bandwidth and the latency, a number of outstanding packets. Okay, so in any case, let's draw this here. So we got New Zealand, we got the California endpoint, we got the Chicago, some sort of peering place, and then we have UIC. And so we have a few connections. And how long is the latency here? It's maybe 5 milliseconds to get to the Chicago point of presence that UIC connects to for all of our traffic. And then to get to California was an added, say, 45 milliseconds. And then we had an added maybe 200 milliseconds there, right? Okay, so if we look at the available bandwidth on these links, if I was to talk just to this peering location, to this point of presence, the uplink to there is probably on the order of a gigabit per second, right? Something like that. Nice big fat pipe, and it's all ours. So we can, well, it's all UICs at least. We're not sharing it with any other institutions. So that one's really nice. Okay, and then of course the connection from Chicago to California is even bigger. Right? There's a lot of traffic going from Chicago to California, but we're sharing that one with millions of other users, so probably it's not all that great. And then, okay, and we don't know what's going on here. Let's just say that this is not a really fat pipe for now. All right, this is probably it's a pretty fat pipe, but let's leave it like this for the point of discussion. Okay, so when I start sending here, I have a very good connection to the Wi-Fi access point. Does anyone know sort of what speed I can expect to the access point? 100 megabit per second, something like that. It's not in the gigabits usually, right? So I can feed 100 megabit per second here, and then we get to ACCC, and going out of UIC, it's even faster. So everything I send will make it out of here, right? Even if a lot of other people are using it, you know, I can maybe send at full speed and it'll make it all the way to the Chicago point of presence. And then now we're starting to push, and there's all of the rest of UIC's traffic, and we have all this stuff coming in from UIC, and we want to go to California, and a lot of us actually want to send stuff to California because there's a lot going on there. So maybe not all of it makes it there, but most of it, because it's a really well provisioned link. So if I send at a full speed, maybe, you know, I get like maybe half of my packets make it through here. It would be optimistic of me to think that I can send at the full rate to my Wi-Fi access point, and it makes it all the way to California. And then if I continue, maybe 5% will make it to New Zealand. So that's fine, right? I'll just go, and then whatever makes it, makes it. Or what do you think? It's not good? Why not? We want it all to get, that's true, but I can send more. Right? It's true, it gets difficult when you lose packets, like you have to retransmit them and stuff, but I can just keep track of the retransmit. The computer's doing the work, so who cares? Or?
It doesn't scale well when there's more than one person trying to do the same thing.
It doesn't scale well, why not?
Because if everyone's trying to send as much as they can at once, if hundreds of people are trying to do it at once, then it's going to saturate the line a lot quicker than you're expected.
Yeah, if we're all sending at maximum Wi-Fi rate, then probably I will only get a smaller fraction through here. But in the end, you know, we're sharing it. I get my part, right? What's the problem? There's a real fundamental weakness here. I'm sending packets. They're making it from here. Okay, maybe this Wi-Fi link isn't so precious. But then this link here, the one to the Chicago point of presence, we're paying for this, right? I'm sending a shitload of packets, and then it delivers only some of them. Okay, maybe we only pay for the ones that got delivered this way. But these guys, they don't care what happens to my packets over here on the way to New Zealand. So now I sent, you know, maybe I got 50 megabits through, and here I'm only down to a couple of megabits. So now we've sent 48 megabit all the way to California. And then they drop it on the floor. And there's no accounting for this. It's not like, oh, you get your money back because we dropped it. That's not it. So I'm basically wasting 48 megabit of capacity because I'm sending too fast. And that's not just all wasting for me, because I'm not paying for it, but I'm wasting it for everyone else who could have used it to talk to, I don't know, Dropbox or something in California. Right? So, yeah, the problem is waste. It's not, I guess, maybe one could call this work conserving. I really should adjust my transmission rate to whatever is the minimum of all the links. What can I get through the whole way? Right, so if I was to send initially, if this was now, if I can get 2 megabits out of this, if I send 2 megabits from here to the Wi-Fi access point and so on, then we're going to have a nice thin line going all the way through, no packet losses, or few packet losses, makes my life easier, and everyone else gets more bandwidth to play with. So that's the goal. So, okay, we were able to measure the latency pretty easily. We send a packet and we get a packet back. How do we measure bandwidth? Here's an idea. Send at maximum rate and see what gets through. Okay, someone likes it.
Can you slowly up the rate until you start to see packets?
This would be better, right? If we start at the maximum rate, probably you're going to have lots of waste while you're starting it up. And there's a lot of people out there using the internet. If they're all doing that, every time they make a connection, it's going to be problematic. So much better that we're conservative. We start at a slow rate and increase it. Ideally, very slowly, right? We want to be really conservative here. So we should start with 1 packet, I think. Right, we send 1 packet. If it makes it through, good. Right, we get the ACK, and then what? 2. It's the next most conservative, right? So let's do 2. All right, next one. And then it's 4? Okay, so that's a huge difference between 3 and 4 here. All right, we could have gone to 3. 3 would be the way to be the most conservative. 4, I don't know. But okay, the advantage, what's the trade-off there, right? We could go with 3. Why don't we go with 3? Yeah.
Because then you're gonna, the potential that you can get to, you're likely never gonna get to it because you're increasing so slowly.
Yeah, so we have a long latency, right? We get to increase by 1 packet every round trip time. So we send 2 and then we wait for a quarter second, and we send 3, wait for a quarter second. This is gonna take a while before we get to, well, it depends, right? If our latency is small and our bandwidth is small, then it's really, really easy. Like, oh, well, what do we calculate to Europe, right? We needed to go to fill some pipe. There was a pretty small pipe, but we said 8 packets, right? So how long is that going to take? It's going to take 8 round trip times, and then we're at maximum rate. That's totally fine. But what if you have a gigabit pipe to New Zealand, right? Then you have a real problem. Now it's going to take you all day to get to the maximum rate. So we need a nice trade-off, and we'll have to get to that next time. But quickly, the general idea is double, 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 double until you lose something. Now we get like a binary search, right? And you lose something, and then you change your mind, and then we go carefully, right? 1 at a time. Right? That's the general idea. We will try to simulate that maybe next time, or see what the TCP does for real. And yeah, I'll see you on Wednesday. Yeah, question.
Project still due Wednesday?
Oh, did it say Wednesday? No. It should be. Let's make it next Friday. Yeah.
This week's Friday, but next week's Friday.
Yeah. Because I still haven't put out my server tonight. I'll try.